Chapter 5: Arachidonic Acid and the Initiation of Inflammation. Arachidonic acid sits near the center of inflammatory biology because it is one of the body's main stored substrates for rapid defensive signaling. It is not floating around as a random irritant waiting to cause trouble. It is built into membrane phospholipids, especially at positions where it can be released when the cell detects injury, threat, mechanical disruption, immune activation, or other stress signals. That placement is important because it means arachidonic acid is part of the body's prepared response system. The membrane is not only a boundary and not only a signaling surface. It is also a loaded reservoir of potential inflammatory chemistry. When the right trigger arrives, enzymes such as phospholipase A2 liberate arachidonic acid from a membrane, and once released it becomes available to cyclooxygenase, lipoxygenase, and related enzymatic pathways that rapidly generate a large family of mediators. Those mediators are what give inflammation much of its early direction, force, vascular character, and local urgency. To understand why inflammation starts the way it does, arachidonic acid has to be understood first as stored architecture and then as mobilized instruction. This point matters because inflammation is often described as if it begins with immune cells deciding to become aggressive. In reality, the sequence is more physical and more immediate. A tissue is disturbed. Receptors sense damage-associated signals, microbial signals, oxidative stress, or mechanical disruption. Membrane-associated enzymes are activated. Arachidonic acid is released from phospholipids. Enzymatic conversion begins. Blood vessels change tone. Endothelial permeability shifts. Platelets may become more active. Pain signaling is amplified. Immune cells are recruited. What looks like one event called inflammation is actually a coordinated cascade launched from stored lipid substrate. That does not make arachidonic acid a pathological molecule. It makes it one of the body's main acute response materials. Without it, the organism would struggle to generate the speed and local intensity required to contain injury, respond to infection, or coordinate early tissue defense. Inflammatory initiation is not an accident. It is a built-in capacity, and arachidonic acid is one of its key fuels. The reason arachidonic acid is so effective in this role is that it occupies a middle ground the body can use efficiently. It is reactive enough to be rapidly converted into potent local mediators, but stable enough to remain stored within membranes until release is needed. Once liberated, it enters pathways that produce prostaglandins, thromboxanes, leukotrienes, lipoxins, and related eicosanoid molecules. Each of these mediator families influences different parts of the inflammatory sequence. Some increase vascular permeability, so plasma proteins and immune cells can reach the site of disruption. Some alter vasodilation or vasoconstriction depending on tissue context and timing. Some recruit leukocytes and intensify chemotaxis. Some increase pain sensitivity, so damaged tissue is protected behaviorally. Some affect platelet aggregation and hemostatic coordination. In other words, arachidonic acid does not create one generic inflammatory signal. It creates a language of local control, and that language is how the body translates tissue disruption into organized reaction. This is why arachidonic acid has to be discussed carefully. In popular nutrition language, it is often treated as if it were synonymous with harmful inflammation, but that interpretation confuses function with excess. The body needs initiation chemistry. If blood vessels could not change permeability, immune cells could not be recruited effectively, and damaged tissue could not generate a local alarm state, defense would fail before resolution was ever relevant. The real problem begins when arachidonic acid-derived initiation becomes chronically dominant, when the substrate reservoir is disproportionately weighted toward escalation, or when later phases of inflammatory sequencing fail to shut down the reaction once the useful work has been done. Arachidonic acid is not the problem because it starts inflammation. The problem is what happens when starting becomes easier than finishing. The structural origin of arachidonic acid also explains why inflammatory tone is partly predetermined before any acute event occurs. A tissue that has incorporated substantial arachidonic acid into its membrane phospholipids is not simply resting in a neutral state. It is holding a certain kind of future signaling potential. If phospholipase activation occurs, that tissue is prepared to generate a particular range of eicosanoid outputs. This means chronic remodeling of membrane composition changes not only how the membrane behaves mechanically and electrically, but also what kind of inflammatory response becomes likely under stress. The tissue carries its future reaction within its own surface structure. A membrane more enriched in arachidonic acid is more prepared for strong initiation chemistry. That can be useful when acute responsiveness is needed. It becomes a liability when stress is chronic, oxidative damage is ongoing, immune activation is frequent, and the body repeatedly draws from the same initiation-heavy reservoir without adequately rebuilding the larger sequence toward closure. The vascular effects of arachidonic acid-derived signaling show how quickly this chemistry can alter local reality. Prostaglandins can expand or contract vessels depending on subtype and context. Endothelial surfaces can become more permissive, allowing immune cells and plasma factors to exit circulation and enter tissue. Platelet-derived thromboxanes can influence aggregation and clot formation. These are not minor side effects of inflammation. They are core parts of the body's decision to convert a stable tissue environment into an acute response zone. Once these vascular shifts begin, the tissue is no longer operating under ordinary homeostatic rules. Fluid dynamics change. Cellular traffic changes. Pressure relationships change. Local oxygen delivery and nutrient exchange can change. Pain sensitivity changes. The site becomes metabolically and immunologically different. Arachidonic acid is one of the molecules that makes this transition possible, which is why it has such importance at the very start of inflammatory events. Pain is another major part of this initiation sequence. Arachidonic acid-derived prostaglandins sensitize nociceptors and make tissue disturbance more behaviorally obvious. This is often viewed negatively because pain is unpleasant, but the biology behind it is protective. The body uses pain to alter movement, reduce load on injured structures, and increase awareness of tissue damage or irritation. Inflammation without pain would often lead to continued use of compromised tissue and greater structural injury. Again, the issue is not that arachidonic acid produces pain-related mediators. The issue is whether those mediators remain proportionate to the problem they are signaling and whether the system can later reverse sensitization once repair is underway. When inflammatory sequencing fails, pain remains after utility has ended. At that point, the body is no longer using arachidonic acid-derived signals intelligently. It is repeating initiation chemistry without successfully completing the transition into restoration. The immune recruitment side of arachidonic acid biology is equally important. Leukotrienes and related mediators help direct immune cells toward disturbed tissue, increase adhesion interactions, and intensify local defensive behavior. This is useful when there is genuine infection, tissue damage, or a need for rapid containment. But because these mediators can strongly amplify local immune traffic, they also contribute to the shift from proportionate acute inflammation into chronic inflammatory persistence when regulatory balance is lost. A tissue repeatedly generating arachidonic acid-derived recruitment signals can remain stuck in a state of cellular arrival without efficient debris clearance, resolution signaling, and return to baseline. The immune system then appears overactive, but in structural terms the tissue is repeatedly drawing from an initiation-centered substrate pool and failing to transition into the later phases that would complete the job. This is one reason arachidonic acid has to be understood inside a sequence rather than in isolation. It belongs to the beginning of inflammation far more than to the end. It helps establish the early local conditions of defense. It changes vascular access, pain sensitivity, platelet behavior, and immune recruitment. It is part of how the body says something is wrong here and resources need to move now. That role is legitimate and necessary. But if a sequence stops there, initiation becomes self-damaging. Tissues remain permeable too long. Nociceptors remain sensitized too long. Immune cells remain recruited too long. Reactive oxygen species and proteolytic activity remain elevated too long. At that point, the body is not suffering because arachidonic acid exists. It is suffering because initiation has been decoupled from resolution. This chapter, therefore, establishes a crucial principle for the rest of the book. Inflammation begins with lipid mobilization for membranes, and arachidonic acid is one of the main early substrates that gives inflammation its force. That makes it essential, not optional. But because it is essential, it also has to be matched by equally competent systems that can contain, redirect, and terminate the response once the need for escalation has passed. Arachidonic acid explains how the body launches defense. It does not explain how the body safely exits defense. That distinction is where much of modern chronic illness begins. The organism is still capable of initiating, is no longer as capable of completing. Once that happens, arachidonic acid stops looking like part of a healthy sequence and starts looking like chronic inflammatory burden, even though the deeper failure is not in the existence of initiation chemistry itself. The deeper failure is in what does or does not come after it. Omega-6 as an activation signal. Omega-6 functions as an activation signal because it helps load tissues with the substrate needed to begin rapid response when disturbance occurs. This does not mean omega-6 itself is always circulating as an alarm molecule. It means omega-6 derived fatty acids, especially arachidonic acid, are built into membrane phospholipids in a way that prepares the cell for future activation. The signal is stored before it is expressed. When receptors detect tissue injury, immune challenge, oxidative stress, mechanical disruption, or other forms of danger, phospholipids release omega-6 derived substrate from the membrane, and that release creates immediate access to a family of mediators that can change vascular tone, increase permeability, recruit immune cells, amplify pain sensitivity, and intensify local defensive activity. Omega-6 is therefore an activation signal in reservoir form. It is part of how the body keeps early inflammatory potential embedded in tissue architecture rather than waiting to build it from scratch after the problem has already begun. This stored activation capacity is one reason omega-6 is biologically necessary. A body that could not rapidly generate local inflammatory signaling would be slow to contain injury, slow to recruit immune help, slow to alter blood flow at damaged sites, and slow to protect tissue behaviorally through pain and sensitization. Acute defense requires molecules that can move quickly and act locally, and omega-6 derived mediators provide much of that early language. Prostaglandins, leukotrienes, and thromboxanes do not emerge from nowhere. They emerge from omega-6 substrate already positioned inside membranes, ready for mobilization once threshold is crossed. That makes omega-6 less like a generic dietary fat and more like a preloaded ignition system. Under the right conditions, it helps the body say something is wrong here, pay attention here, send resources here, and change behavior here. What makes omega-6 especially powerful in this role is that it links structure to urgency. A membrane enriched in omega-6 derived substrate is not just a membrane with different physical properties. It is a membrane carrying a certain future inflammatory bias. Once activated, it can rapidly generate signals that expand a reaction outward from the initial point of disturbance. Blood vessels can widen or change permeability. Endothelial surfaces can become more adhesive to immune cells. Platelets can become more reactive. Pain thresholds can drop. Immune cells can be drawn into tissue with greater force. This is how local tissue disruption becomes organized inflammation rather than isolated biochemical noise. Omega-6 gives the body a way to convert damage detection into a coordinated state change. Activation is not just turned on. It is assembled through mediator families built from omega-6 substrate already present in the membrane. This is also why omega-6 should not be described as inflammatory in a purely negative sense. Inflammation at the initiation stage is not inherently pathological. It is one of the main ways the body protects itself. Without it, tissue damage would spread more easily, microbial intrusion would be less contained, and repair would begin too late or too weakly. Omega-6 derived signaling is part of how the body prioritizes a problem. It makes the site metabolically louder. It changes blood flow, sensation, cellular traffic, and biochemical activity, so the tissue is no longer treated as normal background terrain. The body requires this activation logic. The problem begins only when activation continues after it has served its purpose, or when the membrane reservoir has been remodeled so heavily toward initiation that even modest disturbances produce excessive inflammatory output. That shift from useful activation to chronic overactivation is where context becomes critical. Omega-6 as an activation signal is healthy when it appears in proportion to real need and when the organism retains the ability to move into later stages of inflammatory sequencing. If the tissue can recruit, contain, clear, and then resolve omega-6 has done its job. But if the body repeatedly mobilizes omega-6 derived substrate in response to ongoing metabolic stress, gut-derived immune irritation, oxidative burden, mechanical strain, or unresolved tissue damage, then activation becomes a chronic state rather than a temporary phase. The membrane remains loaded with initiation material, the system keeps drawing from it, and the person begins living inside repeated low-grade alarm signaling. At that point, omega-6 is not acting as a faulty molecule. It is acting as an overused one inside a sequence that is no longer being completed. This is one of the main reasons the modern conversation around omega-6 becomes confused. People see the effects of chronic inflammatory activation and assume omega-6 itself is the enemy. That interpretation mistakes function for imbalance. The body needs omega-6 because it needs to be able to respond rapidly when something goes wrong. But a body built under chronic stress, oxidative instability, poor resolution capacity, and disproportionate membrane loading with omega-6 derived substrate will naturally behave as though activation is easier than recovery. The real issue is not that the ignition system exists. The issue is that the brakes, steering, and shutdown sequence are no longer proportionate to the power of ignition. Omega-6 becomes dangerous when activation dominates the organism's operating style. The signaling role of omega-6 also extends beyond obvious inflammation. Activation includes vascular change, platelet behavior, nociceptive sensitization, epithelial response, immune recruitment, and shifts in tissue metabolism. These are all part of the body's decision to move from ordinary maintenance into active defense. In that sense, omega-6 is not simply a trigger for swelling or redness. It helps move tissue into a different operational mode. The body reallocates attention, resources, and biochemical priority. That mode is useful when short-lived and harmful when persistent. It is adaptive when paired with completion and destructive when left open-ended. Omega-6 derived activation is therefore best understood as necessary early-phase biological force. It gives the system the capacity to react decisively. The danger appears when decisiveness becomes default rather than temporary. Seeing clearly omega-6 as an activation signal is one of the central truths of inflammatory biology. The body builds part of its emergency language directly into its membranes, and omega-6-derived fatty acids are a major part of that language. They prepare tissues to escalate when escalation is justified. They help transform cellular detection into tissue-wide response. They make defense possible. But because they are so effective at beginning the sequence, they also reveal the deeper problem in chronic illness. Many people still have strong activation capacity. What they lack is equally strong completion capacity. The body can still say go. It has become less able to say enough. Eicosanoid cascades. Eicosanoid cascades are the biochemical expansion system that turns membrane disturbance into organized inflammatory action. They begin when polyunsaturated fatty acids, especially arachidonic acid, and in some contexts CPA, are released from membrane phospholipids by phospholipase activity after a trigger has been detected. That trigger may be tissue injury, immune receptor activation, oxidative stress, mechanical damage, endotoxin exposure, cytokine signaling, ischemia, or another form of biological disruption. Once the fatty acid is liberated from the membrane, it enters enzymatic pathways that convert stored structural substrate into highly active local mediators. This is what makes the term cascade useful. The system does not produce one signal and stop. It branches outward into multiple mediator families, each affecting blood flow, vascular permeability, pain sensitivity, leukocyte trafficking, platelet behavior, smooth muscle tone, oxidative activity, and the timing of the inflammatory sequence itself. The cascade is how the body scales up a local trigger into a tissue-level state change. The first major feature of an eicosanoid cascade is speed. The body does not need to synthesize an entirely new structural platform before reacting. The substrate is already present in the membrane, and the enzymes required for conversion are either present, inducible, or rapidly mobilized. That allows an injured or activated tissue to move quickly from detection into action. A membrane phospholipid loses arachidonic acid. Cyclooxygenase enzymes may begin converting that arachidonic acid into prostaglandin intermediates. Lipoxygenase pathways may begin producing leukotriene or lipoxin precursors. In some tissues, cytochrome-dependent routes contribute additional oxidized lipid products with their own local effects. The tissue then stops behaving like resting tissue and starts behaving like activated tissue. Vessels change. Immune traffic changes. Sensory thresholds change. Cellular recruitment begins. The key point is that the eicosanoid cascade is not separate from membrane biology. It is membrane biology becoming inflammatory instruction. The cyclooxygenase branch is one of the main early arms of this cascade. Through COX enzymes, arachidonic acid is converted into unstable intermediates that are then processed into prostaglandins, prostacyclin, and thromboxanes. These are not redundant molecules. They handle different parts of the local response. Some prostaglandins increase pain sensitization, alter vascular tone, raise local temperature, or influence immune activity. Prostacyclin can affect vascular behavior and platelet restraint in certain settings. Thromboxanes push in a different direction by promoting platelet aggregation and influencing vascular constriction. The meaning of the cascade, therefore, depends on tissue context and mediator mix. The body is not simply making inflammation stronger, it is changing the operating rules at the site. It is determining whether blood should flow more freely, whether clotting should increase, whether nerves should become more sensitive, whether local tissue should swell, and whether immune cells should interpret the area as an active zone requiring attention. The lipoxygenase branch extends the cascade into immune recruitment and inflammatory amplification. Through lipoxygenase activity, arachidonic acid can be converted into leukotrienes and related compounds that intensify leukocyte chemotaxis, alter bronchial tone, increase vascular permeability, and strengthen the recruitment logic of acute inflammation. This is one reason inflammatory tissue begins attracting more cells into itself once the cascade is underway. The tissue is not merely damaged, it is broadcasting. Leukotrienes help generate that broadcast by increasing the biochemical force pulling immune cells toward the site and by reshaping the local environment so that immune traffic becomes easier and more sustained. This is useful when real containment is needed. It becomes destructive when the recruitment phase stays active longer than the problem justifies, or when the tissue never transitions cleanly into later stages of debris clearance and shutdown. The cascade is also self-amplifying in practice, even when it is tightly regulated in design. Eicosanoid production can increase vascular permeability, and increased permeability can increase exposure of tissue to circulating immune components and inflammatory signals. Recruited immune cells can generate additional cytokines, reactive oxygen species, proteases, and lipid mediator production, which can further stimulate phospholipase activity and additional arachidonic acid release from nearby membranes. Pain sensitization changes behavior, which alters tissue use and sometimes tissue loading. Platelet activation changes microvascular conditions. Endothelial shifts alter trafficking patterns. In this way, the cascade does not simply spread chemically. It changes the local physical environment so that more inflammatory events become likely. That is why initiation can become disproportionate so easily in a stress system. Once the cascade starts, it creates conditions that favor its own continuation unless counter-sequencing mechanisms come online. This is where balance becomes crucial. Eicosanoid cascades are supposed to be phase-specific. Their purpose is to initiate and organize early response, not to remain dominant indefinitely. Arachidonic acid-derived eicosanoids are especially powerful because they help the body create urgency, but urgency is only useful if it is time-limited. Once microbial containment, hemostasis, or acute damage signaling has been established, the tissue needs to move toward clearance, repair, and reduction of collateral injury. If the eicosanoid cascade keeps running without appropriate containment, the same mediators that originally protected tissue begin contributing to pain persistence, vascular dysfunction, leukocyte overrecruitment, oxidative injury, and barrier breakdown. The problem is then not that the cascade exists. The problem is that it has remained in command after the job requiring command has changed. EPA can also enter eicosanoid pathways, and this matters because it slightly alters the character of the cascade. EPA-derived eicosanoids often have different biological potency and different downstream consequences than their arachidonic acid-derived counterparts. This does not erase inflammatory initiation, nor should it. It changes substrate competition and can shift the mediator field toward a somewhat different signaling profile. That shift is part of why omega-3 incorporation matters upstream. The membrane reservoir partly determines which version of the cascade becomes available once phospholipase activity begins. A membrane storing more EPA relative to arachidonic acid is not identical in inflammatory potential to one storing mostly arachidonic acid. The difference is not absolute replacement. It is altered probability within the cascade. The tissue has slightly different words available when it begins speaking inflammatory language. Eicosanoid cascades also explain why chronic disease can feel like repeated false emergency. The body does not need a dramatic acute injury every day to keep these pathways partially active. chronic endotoxin exposure, adipose-derived inflammation, barrier dysfunction, oxidized lipids, repetitive mechanical strain, unresolved infection, mitochondrial stress, and persistent cytokine signaling can all maintain enough phospholipase activity and enzymatic throughput to keep eicosanoid output elevated or repeatedly re-triggered. The person then lives inside a body that keeps converting membrane substrate into activation chemistry. Pain persists. Vascular tone becomes less stable. Immune cells continue arriving. Recovery remains incomplete. The body acts like it is still in the early middle phase of response because biochemically, it often is. This is why understanding eicosanoid cascades is so important for the rest of the omega-3 and resolution discussion. They show how initiation actually happens in material terms. Membrane structure is disrupted or signaled. A fatty acid is released. Enzymatic branches convert that fatty acid into local instructions. Those instructions alter the tissue environment and recruit a larger defensive state. Nothing about this is abstract. It is physical, stored, triggered, and amplified. Eicosanoid cascades are the mechanism by which lipid architecture becomes inflammatory behavior. They explain why the body can respond so quickly, why imbalance becomes so consequential, and why changing membrane composition over time can alter not only structural behavior, but the very language the body uses when something goes wrong. Necessary versus chronic inflammation. Inflammation is not a design flaw. It is a controlled emergency program built into tissue so the body can respond when normal conditions are broken. Without it, injury would spread more easily, pathogens would gain territory more easily, damaged structures would persist without coordinated cleanup, and repair would begin too late or too weakly. Necessary inflammation is the form that serves a clear purpose and remains tied to sequence. It begins when tissue disruption, infection, toxic exposure, or structural injury creates conditions that cannot be handled by ordinary maintenance alone. Local vessels change behavior. Permeability shifts. Immune cells are recruited. Damaged material is identified. Pain sensitivity may rise, so the injured area is protected from further use. Oxidative chemistry may increase because microbes or damaged components have to be contained and dismantled. This is not pathological simply because it is uncomfortable. It is the body moving from background maintenance into active defense because the situation requires more than quiet homeostasis can provide. What makes necessary inflammation healthy is not the absence of force. It is the presence of direction. The response is matched to a real disturbance, and each phase helps prepare the next one. Initiation chemistry opens access. Recruitment brings in the machinery. Clearance removes threats and debris. Then the system shifts. The same tissue that intensified blood flow, immune traffic, and pain signaling has to begin reducing those outputs once their job is done. Macrophages change behavior. Dead cells and spent inflammatory material are cleared. Barrier integrity begins to restore. Pro-inflammatory mediator dominance gives way to pro-resolving signaling. Pain sensitization declines. Vascular permeability tightens back down. Tissue no longer behaves like an emergency zone because the emergency sequence has been completed. Necessary inflammation is therefore not defined by mildness. It is defined by completion. It does work, then it exits. Chronic inflammation is different because it has lost that sequence. It may still use many of the same molecules and cell types, but it no longer behaves like a temporary program moving toward closure. Instead, the body remains trapped in repeated initiation, incomplete clearance, unresolved tissue signaling, or ongoing low-grade recruitment. The system keeps spending resources without finishing the task those resources were meant to accomplish. Blood vessels may remain too permissive. Nociceptors may remain sensitized. Immune cells may keep arriving while debris clearance stays inefficient. Oxidative stress may continue damaging tissue faster than repair can stabilize it. The membrane reservoir keeps being drawn upon for inflammatory signaling, but the later phases that should terminate the response never fully dominate. At that point, inflammation stops being a response to a contained event and becomes part of the tissue's background operating style. This is why chronic inflammation is not simply more inflammation. It is inflammation that has become structurally mismanaged. The body still knows how to start. In many cases, it is very good at starting. The deeper failure is that the body is no longer coordinating the transition from activation to resolution. A tissue may continue generating arachidonic acid-derived signals because the trigger has not truly been removed, because barrier dysfunction keeps supplying new immune stimuli, because mitochondrial stress keeps generating danger chemistry, because damaged membranes keep releasing reactive substrate, or because the signaling environment has been remodeled to favor escalation more than completion. In each case, the result feels similar. The response remains open. The body lives in a state of unfinished defense. That unfinished state changes the meaning of symptoms. Unnecessary inflammation, pain, swelling, fatigue, heat, and local sensitivity are part of a temporary biological logic. They help alter behavior, allocate resources, and protect tissue during a defined period of work. In chronic inflammation, the same outputs no longer reflect an intelligent time-limited sequence. They become evidence that the system has failed to return to baseline. Pain persists after useful protection has ended. Fatigue continues because the body remains metabolically expensive. Swelling continues because vascular control remains altered. Immune signaling continues because the tissue is still being read as unfinished business. The body is no longer simply defending itself. It is being held inside defense. This distinction is one of the most important in modern health because many people try to suppress all inflammation as though the goal were silence. Total suppression is not the solution. A body incapable of mounting necessary inflammation would be weak, slow to recover, and poor at containing real threats. The goal is not to abolish inflammatory capacity. The goal is to preserve acute inflammatory competence while restoring the ability to resolve. That requires more than blocking one mediator. It requires membranes that can support proper signaling sequence, immune cells that can shift phenotype after acute work is done, barrier systems that stop feeding repeated triggers into tissue, mitochondria that stop generating excess distress signals, and a lipid substrate environment that does not keep loading the system toward endless initiation. Resolution is not the absence of inflammation. It is the successful completion of inflammation. This is where omega-3 and resolution biology becomes so important in the broader argument of the book. Chronic inflammation is often treated as though the body has too much inflammatory force and too little suppression. In many cases, the more accurate description is that the body has enough force to begin but insufficient structural and signaling conditions to end well. Necessary inflammation depends heavily on omega-6 derived initiation chemistry because early defense must happen quickly. Chronic inflammation develops when that early chemistry is repeatedly mobilized without sufficient downstream transition into cleanup, restraint, and tissue restoration. The body does not only need to turn inflammation on correctly. It needs to turn it off correctly, and not by bluntly disabling the immune system, but by completing the biological job in the right order. Seen clearly, necessary and chronic inflammation are not distinguished by whether inflammation exists. They are distinguished by whether the sequence remains intelligent. Necessary inflammation is specific, proportionate, and finite. Chronic inflammation is repetitive, poorly terminated, and structurally self-sustaining. One protects tissue by temporarily changing its state. The other damages tissue by keeping that state active after its useful phase has ended. That is why the real question is never simply how much inflammation the body has. The deeper question is whether the body still knows how to move from alarm to repair without getting trapped in alarm itself. The problem of overinitiation. The problem of overinitiation begins when the body becomes too ready to start inflammatory defense and not ready enough to control where that defense stops. Initiation is supposed to be sharp, local, and temporary. It exists to mark disruption, change tissue conditions quickly, recruit the right cellular machinery, and create enough force to contain a problem before it spreads. But when the threshold for activation drops, or when tissues are repeatedly loaded with triggers that keep crossing that threshold, initiation stops behaving like an emergency response and starts behaving like a default posture. The body begins reacting to ordinary biological friction as though it were exceptional danger. Membranes release substrate too easily. Receptors amplify too quickly. Vascular changes happen too often. Immune cells are summoned too readily. Pain pathways stay too close to the surface. The result is not simply inflammation. It is a body that has become primed to enter inflammation faster than it can justify or complete. This can happen for several reasons at once. Membrane composition may become biased toward activation-heavy substrate, especially when arachidonic acid-rich signaling potential is repeatedly mobilized without sufficient counterweight from resolution capacity. Barrier tissues may begin leaking signals that should have remained outside, forcing the immune system to respond to a steady stream of low-grade provocation. Mitochondria under stress may generate danger chemistry that keeps tissues biochemically loud even in the absence of obvious injury. Oxidative damage may alter membranes so they become easier to disturb and more likely to release inflammatory substrate. Adipose tissue may add background inflammatory pressure through chronic excess signaling. Repeated mechanical strain, poor recovery, persistent endotoxin exposure, unresolved infection, or metabolic instability can all keep the initiation machinery partially engaged. None of these conditions require dramatic acute injury. They only require enough repeated disturbance to teach the body that activation is normal. Once overinitiation takes hold, the entire inflammatory sequence becomes distorted. Early-phase chemistry starts appearing in places, and at times where it should have remained minimal. The tissue becomes more vascularly reactive, more permeable, more sensitive, and more crowded with immune traffic. Nociceptors are sensitized more often, so discomfort appears sooner and lasts longer. Cytokines and eicosanoids are generated more readily, which feeds forward into additional phospholipase activity and more substrate release from nearby membranes. The tissue environment becomes easier to ignite with each cycle because initiation itself remodels the local structure. Oxidative stress increases. Membrane damage increases. Barrier precision declines. Cellular debris accumulates faster than it can be cleared. The body is no longer merely responding to a problem. It is becoming easier to trigger into response as part of its new baseline. This creates one of the most important asymmetries in chronic illness. Starting inflammation is usually easier than finishing it. Initiation chemistry is fast, forceful, and heavily supported by built-in substrate reservoirs. Resolution is more demanding. It requires proper timing, phenotype switching in immune cells, successful clearance of damaged material, intact barrier restoration, enough metabolic energy to rebuild, and access to the signaling environment that tells the body the acute phase is over. When overinitiation dominates, those later steps never gain full control. The body keeps arriving at the early middle phase of inflammation and re-entering it before closure has taken place. In practical terms, this means the organism is always spending on defense and never fully collecting on repair. The tissue becomes trapped in repetition. Overinitiation also changes how the body interprets normal life. Inputs that should have been handled quietly begin generating disproportionate reaction. Food components provoke more immune attention than they should. Exercise creates more inflammatory residue than the recovery systems can clear cleanly. Minor stressors trigger outsized systemic consequences. Mechanical pressure produces longer-lasting pain. Small injuries take too long to stop feeling active. The immune system becomes less discriminating because the thresholds governing activation have shifted downward. This does not mean the body has become irrational. It means the surfaces and signaling systems through which it reads the world have been remodeled into a more defensive state. Reality begins to look more threatening to the organism because its membranes, receptors, and mediator reservoirs are configured to escalate quickly. This is one reason simple anti-inflammatory suppression so often disappoints. If the deeper problem is overinitiation, then silencing one branch of inflammatory output may reduce symptoms temporarily without changing the tissue state that keeps generating new activation. The body remains easy to trigger. The membrane reservoir remains biased toward early-phase signaling. Barrier problems continue feeding immune provocation. Mitochondrial stress continues generating internal alarm chemistry. Oxidative instability continues lowering the threshold for membrane disruption. The visible fire is dampened, but the ignition conditions remain intact. This is why chronic inflammatory states often return as soon as suppression is removed. The sequence was not completed. The tissue was only muted while the architecture of overinitiation remained in place. The role of omega-6 biology becomes especially important here. Omega-6 derived substrate is necessary for acute defense, but when tissues are repeatedly drawing on that substrate without adequate resolution and reconstruction, the body becomes too fluent in the language of escalation. It knows how to increase permeability, recruit cells, amplify pain, and alter vascular tone. It becomes less capable of stopping those actions once they are no longer useful. Overinitiation is therefore not just a signaling problem. It is a structural memory problem. The tissue keeps carrying the material and the interpretive habits of early-phase defense. Each new trigger enters an environment already prepared to overreact. This is where the next part of the lipid story becomes essential. A body suffering from overinitiation does not just need less inflammation in the blunt sense. It needs restoration of threshold, proportion, and sequence. It needs membranes that are less easily pushed into reactive instability. It needs less constant release of activation substrate and better access to the lipid mediators that help terminate inflammatory programs once the necessary work has been done. It needs immune behavior that can still mobilize decisively when required, but no longer treats every disturbance as grounds for prolonged escalation. Overinitiation is the problem because it turns an intelligent defense system into a chronic mode of operation. The body keeps pressing go, and each time it does, it becomes slightly less able to remember how to stop.